Hi, everybody. Thanks for joining us on this last session of Chandra Data Science. The last science session, I should point out, because next week we have our self-organized tutorials, 2 days of Bayesian X-ray analysis, starting at 9 a.m. Eastern Day, EDT, UTC -4, August 30th, 31st, and a 3 ml tutorial on September 1st. Following each of those tutorials on those respective days, we have tutorials organized by our CXE team on advanced things that you can do with DS9, science with a Chandra Science catalog, source catalog, and spectral analysis with Sherpa. So if you're still interested in those, you can find the sign up form in your email or in the Slack channel on software. This is our last session. We have a light but very interesting session to close on. Our first speaker is Anna Ogorzalek, who is coming to us from the NASA Goddard Space Flight Center and University of Maryland, College Park. And they're going to talk to us about constraining the power of X-ray wind in NGC 4051, a Bayesian approach. Anna, feel free to share your slides when you're ready. And you're muted right now.
Okay, can you hear me and see me?
Yes, I can. Take it away.
Okay. So hello, everyone. Thank you for joining the very last session of this wonderful workshop. Today, I want to talk to you about a new way of analyzing high-resolution X-ray spectra of AGN outflows with a Bayesian approach, which allows us to extract new and exciting information from the data. I will demonstrate this by focusing on the X-ray detected wind present in Seyfert galaxy NGC 4051. But first, let's put things into astrophysical context. We have realized about 2 decades ago that most, if not all, galaxies harbor supermassive black holes in their centers. If these black holes are actively accreting, we call them active galactic nuclei, or AGN. We believe that AGN, which are efficient at accreting matter, look like the artist's impression that is shown here. We see the matter falling onto the black hole via the accretion disk. At the same time, we see matter that can be ejected from the system either via highly collimated jet or an outflow that covers a wide solid angle. This, of course, is a close-up of a supermassive black hole environment. And if we zoom out of the whole galaxy, we wouldn't actually see any of these structures. This is not surprising, since in terms of size, the black hole is 8 to 9 orders of magnitude smaller than the galaxy, which is just like comparing a quarter coin to the size of the Earth, while the black hole mass is roughly 1,000 times less than the stellar mass of the galactic bulge. However, when we compare their energetic outputs, the black hole accretion energy can actually exceed the binding energy of the galactic bulge by more than 100. So even if a small fraction of this accretion energy couples to the galactic gas, it could completely push it out and destroy the galaxy. But this does not happen, right? We do see many galaxies in our universe. So then, do the black holes and galaxies interact? And if so, how? So there are many observational clues for how AGN affect their hosts. For instance, the currently flavored cosmological model, Lambda CDM, precisely predicts the number of dark matter halos of a given mass. Converting to baryons, we can predict how many galaxies of a given mass we should see, which is shown here on the left with the straight gray line. The observed galaxy number, which is shown with black data points, falls short of this prediction, especially for the highest mass systems, which also tend to host the largest supermassive black holes. Further, there is an empirical relationship between the black hole mass and the velocity dispersion of the stars in the galactic bulge, which spans orders of magnitude, which suggests to us that galaxy and black hole growth could regulate each other. All of these examples can be interpreted as black hole galaxy co-evolution, but they can also point towards a common factor driving the two, as for example, similar relationships could result from merger histories of galaxies. The real key evidence that supports the existence of a galaxy-black hole link is the fact that we observe in many, many local and faraway objects clear signatures of AGN feedback taking place. And you've probably guessed that one of these observational evidence are AGN winds. In fact, many supermassive black holes have been found to drive powerful wide-angle outflows, which can carry significant amounts of mass and energy. These outflows show velocities from hundreds to tens of thousands of kilometers per second. Inferred mass loss rates of up to hundreds of solar masses per year can easily affect accretion onto the black hole, as well as clear the galaxy out of gas that could otherwise have formed stars. On galactic kiloparsec scales, these winds are mapped with emission lines in millimeter through UV wavelengths. Closer to the black hole, on parsec scales, we detect them as absorption features in the UV and X-ray bands. But to really determine what is the actual impact of these winds on the host galaxy, we must first understand what is the thermodynamic and kinetic state of the outflowing gas, which sounds simple. And we said before that the wind that originates closest to the black hole, where it can be the hottest and most energetic, is observable in the X-ray band. And since we require precise measurements of the physical properties of the gas, we must use high-resolution X-ray spectra of these AGN winds. Okay, great, problem solved. But now let's actually see what instruments we can use to answer this question. So we can map X-ray spectrographs by looking at the resolving power here on the y-axis over the X-ray band. The gray line already drawn here is the resolving power of a typical X-ray detector as CCD. In orange, I show what resolving power is needed roughly to measure line shifts of the order of 100 kilometers per second, provided high signal to noise data, which is the very least that we need to start making interesting claims about gas dynamics, since typical sound speeds of the gas we are interested in is a few hundred kilometers per second. We immediately see that the typical X-ray CCD does not have sufficient energy resolution for this at all. Thankfully, as we all know, a little over 20 years ago, the first X-ray diffraction gratings were launched into space on board of Chandra X-ray Observatory. Chandra carries two sets of gratings, the LETG, low energy transmission grating, shown here in blue, and HETG, high energy transmission grating, which itself consists of two gratings, the medium energy grating and the high energy grating, shown in green and red respectively. Roughly half a year later, XMM Newton was launched, and XMM carries a set of two reflection grating spectrometers. However, these do not reach the same resolving powers as HETG, as you can see. Chandra and XMM, as we all know, have essentially revolutionized what we know about X-ray universe. However, in my talk, I will focus specifically on the data obtained with HETG, since it currently is, and actually will remain for quite some time, the highest spectral resolution X-ray instrument that's available to us. Okay, so now let's think of the X-ray photons that are emitted by our actively accreting supermassive black hole. We have a physical cartoon of such a system on the left, with the accretion disk and the potential jet, as well as population of hot electrons at the base of the jet, that is called Coronae. Now on the right, we added a typical continuum emission from the system. We have the photon flux on the y-axis and photon energy on the x-axis. And let's talk through how do these emission components originate. So the accretion disk is rather hot, and it emits optical and UV photons, which reach the observer. This is the disk component that is shown in blue. And some of these disk photons, however, will be emitted towards the hot electrons in the corona, where they will be scattered via the inverse Compton scattering process to high energies. What I mean by that is that the disk photons will gain energy from the corona photons and have higher energies than originally. This is the red component, so-called Comptonized coronal power law, and is typically the dominant component of X-ray AGN emission. Then some of these scattered photons will go back towards the disk, where some of them will be further reflected, emerging as a reflected component. and this is shown in green. This components includes bright fluorescent iron K emission at 6.4 keV that's visible even in this rough cartoon. And all of these components constitute a typical AGN X-ray emission. But actually, this picture is somewhat simplified. And in reality, there are also possible relativistic effects on the reflected component. There could be emission by the corona, and so on. But the bottom line here is that there is a strong X-ray continuum emission that originated via different physical processes. So many different physically motivated models are out there that we can potentially use to model it. Okay, so now let's consider what happens when we add a disk wind to this picture. We add winds, shown here conceptually with dashed lines. And as we said before, these outflows originate at the accretion disk further from the black hole than jets, and they cover wide solid angles. So we see that the outflowing gas actually interrupts the continuum radiation on its way to an observer. And spectroscopically speaking, this will manifest itself as absorption features. Depending on how close the gas is to the black hole, because of the disk rotation, these features are typically narrow, in which case we call them warm absorbers, or very broad, in which case they're called ultra-fast outflows, or UFOs for short. Typically, warm absorbers move at few hundreds to thousands kilometers per second, while UFOs can be relativistic. These absorption features carry a lot of information in them. First of all, the depth corresponds to the column density, so amount of material on the path of the light. And then from their Doppler shifts, we can infer their velocities. Finally, by measuring the relative abundances of different ionic species, we can determine the ionization parameter, which in turn is connected via the AGN luminosity to the density and the location of the absorbing material, in this case, the black hole wind. So note that this holds true if we assume that the equilibrium in the absorber is established via photoionization processes. So when we want to model these absorption features, we look at their widths and depths as well as ionization state. And one method to derive the physical properties of the wind is to look at individual absorption features and guess what ionic species they're from. And then based on that, determine their ionization parameter and velocity. However, for a given ionization parameter, so some specific ionization balance, will have many different ionic species present in the gas. So we can utilize all of that information available to us, especially in high resolution spectra, by using self-consistent models of absorption. The self-consistent models also depend on density, allowing us to potentially constrain this crucial physical parameter. The downside here is that such models are usually computationally expensive, which is why this multi-dimensional parameter space is then often explored by grids of models, like the abstract one that I show here on the right. However, oftentimes for one or more parameters, only a narrow range is explored of this parameter space, which can bias the retrieved physical properties of the wind. Often the density of the absorber is, for example, fixed. Another example is focusing on only narrow absorption lines and finding only warm absorbers, or only at broad absorption lines and only finding UFOs. So you only find what you were looking for, and this is why we took a different approach, where instead of fixed grids, we used a Monte Carlo Markov chain process, where Markov chain explores all of the parameter space as illustrated on the cartoon here. Second key feature of this approach is that it provides us with a robust framework for comparing and choosing between different physical models by utilizing deviance information criterion, or DIC for short. So the difference of the DIC of two models, the delta DIC, is basically an approximation of the bias factor. And Johannes Buchner actually gave an excellent talk in session 1 of this workshop about using the bias factor for model selection. So I refer you, if you're interested, to see that talk for more details. Here, let me just briefly show the definition of the DIC that we used, where d of theta is the deviance of a parameter vector theta given likelihood of the data vector y, and PD is the effective number of model parameters which is a measure of motor complexity or flexibility, in other words. But it's not always necessarily just the number of free parameters. So as Johannes explained in his talk already, Bayesian evidence punishes models that are too complex and are basically able to adjust and fit any data points, which I appreciate as a physicist, since it's basically, this approach is basically an implementation of Occam's razor. Hopefully, you also see that the DIC is easy to compute when using Monte Carlo Markov chains, because we have the posterior that's easily available to us. And then to decide between models, we use Jeffrey's scale, which is shown here in the table. So if the delta DIC between two models, so the difference between them is greater than, say, 10, we say that there is a very strong evidence that one model is preferred over the other. We choose delta DAC of 10 as a threshold in our model selection, which is a somewhat conservative assumption. And if we wanted to use lower delta DACs, we would need to perform tailored simulations to test if there indeed is enough evidence to choose between models. And thankfully, the data we look at are so deep and rich in information that we did not need to do that really. Okay, so now let's apply this analysis framework in practice to really understand what wealth of information it can provide. So here we look at one of the deepest, highest signal to noise, high resolution spectra available, the new and archival observation of a Seyfert galaxy NGC 4051 with Chandra HETG, which was observed for 700 kiloseconds in 2016 and 300 kiloseconds in 2008. We first construct a continuum emission model, which is crucial to then properly model the absorption. We test a number of physically motivated models, as we said before, and show the delta DAC values in the table here for illustration purposes. So our analysis shows that beyond the standard coronal power law emission, a neutral reflection is required, modeled by the Silver model, and also relativistic reflection, which originates so close to the black hole that general relativity needs to be taken into account, is required by the data and modeled by the Relsel-D model. This relativistic model for high density disks is able to explain all of the soft excess in the 2016 data, which is an interesting result. But a phenological disk blackbody model is required to explain the 2008 data, possibly because of the limitation of the Relsel-D model. Our analysis, which is clearly shown, our analysis decisively rules out the warm corona modeled, for example, by the NTH comp model as the origin of the soft excess, which is clearly shown by the delta DAC values in the table. So note that the delta DAC values are basically an order of magnitude higher than our already conservative threshold of 10. So having a good model for the continuum emission, we can now model the absorption. So here again, we use the DIC to decide whether or not an additional absorption component is required. We keep on trying to add an absorber until the evidence does not support it anymore, providing a clear cut to what the data is capable of telling us. Furthermore, we consider that the absorber may be in two different physical states. Firstly, we consider the typical photoionization equilibrium where photons emitted in the black hole environment set the ionization balance. We then consider that they might actually also be in collisional ionization balance, where the equilibrium is basically set by gas temperature, something that most analyses don't necessarily take into account. So here again, the DIC can help us decide which motor is more likely given the data, so telling us what is the more likely physical state of the absorber. We have analyzed these two data sets individually and detected 6 absorbers intrinsic to NGC 4051 in the data. Remarkably, these absorbers are independently detected in both data sets spaced 8 years apart. Here I show just a 2 angstrom range of the spectrum with just a few narrow line width absorbers singled out. But the whole spectrum spans 1 to 35 angstrom. And let me emphasize that each outflow component detected imprints tens of absorption features, which are modeled all self-consistently. Using the DIC, we determined that some are in photoionization equilibrium, some in collisional equilibrium, but in both epochs, there are also absorbers where the data actually cannot distinguish between the two ionization balances. Looking at the properties of the absorbers, I show here their velocity on the x-axis, and please note that the scale is logarithmic, and column density, so roughly depth of the features on the y-axis. The 2008 data is shown in blue and the 2016 in red, which allows us to track the evolution of various types of outflow components. We see that the slowest absorbers essentially have not changed, which we expect since they are most likely located far from the black hole, as you may remember from the cartoon I showed you a few slides ago. The fast ones are more variable, which means they're either accelerating or more likely just moving in and out of our line of sight. The fastest absorber, which is moving at an astounding 10% of the speed of light, has been only robustly detected in the new 2016 data. We see it in the older observation as well, but it has not crossed our threshold of significance. Anyway, I hope you agree that tracking this outflow over the next decade or so could be very exciting and extremely rich in information. But going back to the you only find what you're looking for idea, majority of the previous analysis of these data sets focus on the narrow range of the parameter space highlighted here, which means most components, and especially the variability, were missed. Now, when it comes to the physical nature of the outflow, as we said, most of them are photoionized by the strong radiation field of the black hole. For these shown here, our fully open approach crucially does not fix the density, the key parameter, allowing it to be measured. I have highlighted here high density components, which are well constrained and reach densities of the accretion disk. These measurements are extremely helpful in determining the outflow power and its impact on the galaxy. And we see that in this one object, there's high density component, which is located close to the black hole at few hundreds of gravitational radii. For the AGN feedback, the total power the total power of the outflow that's measured is as high as 10% of the bolometric luminosity, making it energetically important for in the context of galaxy evolution. As mentioned before, we also considered usually not explored collisionally ionized absorbers. It turns out that the most statistically significant absorber in both data sets are actually in this physical state. Looking at the 2- and 1-dimensional posteriors on the derived constraints, we see that it's hot at 10⁷ Kelvin and has high column density, moving at about 900 kilometers per second. This component is essentially unchanged between the 2 epochs that we consider. It is detected at high statistical significance, which is illustrated in the bottom figure, where the collisionally ionized absorber is compared to a photoionized absorber that would have been fitted if we did not consider collisional ionization equilibrium. It is clear that the collisionally ionized absorber is much better fit to the data, and then delta DIC between these 2 models of well over 200 confirms this. And this is the first detection of this type of absorber in AGN, which was enabled basically by the model selection capability of the Bayesian framework we've used. The presence of this collisional absorber is interesting, and if found in other sources, will teach us a lot about the physics of these winds. And interestingly, I will mention that in a number of other obscured AGN with obscured centers where grading observations are not possible, a similar temperature collisionally gas is potentially observed via emission on larger spatial scales. One potential origin of the collisionally ionized component that is the part of could be the interaction of the jet with the clumpy ISM in the galaxy disk. Recent simulations by Ryan and Tanner indicate that potentially this process can produce gas that has comparable temperatures and velocities to our measured components. And we're working now on simulations that are dedicated to NGC4D51 to confirm this scenario. Also, based on this discovery, we've won a Chandra grant to study the theoretical implications on the presence of this collisional gas. So stay tuned for further updates. Let me also highlight a side result of this work. I've told you that we detected 6 absorbers that are intrinsic to NGC4D51, but in reality, we also detected one more absorber in both data sets. This absorption is caused by the hot X-ray halo of our own Milky Way, a gas that is close to collisional equilibrium. If not accounted for by the model, unphysical wind components could be fitted. This component arises naturally in our agnostic Bayesian approach, so we did not set out assuming it was present in the data. Notice, Notice how the fit beautifully shows that this absorption is local to the Milky Way, with velocities consistent with 0, and has the viral temperature of the Milky Way, which is about 10 to the 6.3 Kelvin. Because of the depth and high resolution of these spectra, we are also able to place competitive constraints on the metallicity of this gas. I'm not showing them here because they're subject to a debate, so you can check it out in our upcoming publication. Okay, before I tell you what the future holds, let me just quickly summarize the study of X-ray detected outflow in NGC 4051. I have shown you the application of Bayesian framework we have developed, which allowed us to self-consistently model the spectrum and select models in a robust way. As a result, we detected and characterized a number of wind absorbers in NGC 4051 and obtained some of the most precise density constraints to date. As a next step, we will apply our approach to a number of high signal-to-noise, high spectral resolutions HETG datasets, which should provide new constraints on AGN feedback and radiatively efficient AGN. We will start this by analyzing archival data, but something we must all realize is that the future X-ray detectors are really specifically high-resolution X-ray spectrographs. We know that 2 amazing new missions will soon be launched. Firstly, a JAXA-NASA mission CRISM is coming in less than 2 years. And then the ESA-NASA mission Athena will be launched with an even better spectral resolution and massively better collecting area. These missions will give us great resolution and also better photon statistics. It will take Athena less than 10 kiloseconds to deliver spectra comparable to the one I have shown you today, although with lower resolution and lower energies. With the wealth of high resolution and high photon statistics spectra coming in the next decade, we will need to use ever more sophisticated models and be able to tell them apart, which is what I tried to achieve in the presented work. And then further down the line, hopefully we will have Lynx Observatory, which is a concept for a NASA flagship mission. This mission will have both gratings and microcalorimeters and even higher spectral resolution. We will really need to model not only statistical uncertainties on our data, but also systematic uncertainties of our models, response matrices of the instruments, which I know people are already thinking about, which is great. And these are all fairly straightforward things to include within a Bayesian framework. So hopefully I've convinced you that this is something that is worth implementing in your own research. And with this remark, I will move to the conclusions of my talk, where I hope I convinced you that the high resolution spectroscopy offers a unique window onto studying AGN outflows, and that Bayesian analysis is one of the best tools to take advantage of the wealth of information present in deep high signal and high resolution spectra, which are basically the future of our field. So thank you very much, and I can take questions now.
Thank you, Anna. That was an excellent talk. If you have questions for Anna, please add them to the Slack or the Q&A here. I'll read the question that we have for you now from Marcin Markulowicz. Thank you for your talk, and asking, is it possible that a warm absorber is causing something between narrow and broad absorption, or broad absorption itself instead of a UFO as an explanation? For example, a warm absorber plus corona influence.
Okay, so I'm not sure I understand the question, but I'll try to answer best as I can, and if not, we can follow up on Slack. So the division into warm absorbers and UFOs is kind of phenomenological, kind of as people were finding them. I didn't show all the results of this work, but you can check out the paper. Basically, we find, and other people found that too, that in terms of the widths of the lines, we find anything from like 100 to through few hundred, 1,000, few thousand, to I think maximally around like 4,000 or 5,000 kilometers per second. So there is definitely a spectrum of these winds. I will also say that I will agree with the statement that probably not all wide absorbers are UFOs, probably not all of them are relativistic. So yeah, this division is more kind of where people first observe things, but we have to be open to all possibilities and not just kind of focus on what's already been found.
Thank you. And the question is in Slack, so if they want to clarify, they can talk to you there as well. Any other questions for Anna? I have a question for you. So the criteria that you talked about, how it favors simpler models and less complexity. Is it easy to implement elsewhere and outside of the framework that you've developed with, for example, if you're adding lines to a spectral model?
Yes, as long as you have a posterior distributions of your fits, you can basically use it. Absolutely.
So it's something that you can use after you've done your, if you've done like an MCMC fit, you can do it all of your.
Or you can, all you need is the posterior, so you can technically, step through your parameter space and also get the posterior. But yes, and the other advantage is, of course, that this is a simple test, and it's doesn't have the same requirements, the same constraints as like F-test or something, where if your model is that you're checking is that basically non-nested models can be tested like this, but with adding line, which is a nested model, there are no restrictions of overlapping parameter spaces of the two models that one model is not the limit of the other model, which makes other maybe frequentist tools more difficult to use.
Great. And the last question, you mentioned that you saw this high velocity feature only in the 2016 data, but then you did see evidence for it in the 2008. Was that because of you saw it in the 2016? You went to look for it in the?
No. So this is a completely agnostic approach. It was basically, so as I said, we keep on adding components until our criterion says that the next one is not statistically significant. So in both cases, there were more absorbers, but they just like didn't satisfy our delta DIC of 10 criterion. So basically the next component in 2008 would have been the very high velocity component, but that observation is much shorter, and especially because this is a highly ionized component. In the higher energy band, there were significantly less photons. So yeah, it did not cross our threshold. Maybe we could have done kind of more simulations that Johannes Buchner was talking about to kind of calibrate the degree of certainty to which we believe that it's there or not, but we did not choose to do that in this work.
Great. Thanks again for an excellent talk. And that's all the time we have for questions right now. So our next speaker, if you could start sharing your slides. Our next speaker is Stephen Chen, joining us from George Washington University, and is going to talk to us about the importance of distance in automated classification of X-ray sources.
Hello, can everyone see my slides?
Yeah, looks good.
All right. Yeah, so I'm Stephen Chen. I'm a grad student at the George Washington University, and my talk is on the importance of distance in automated classification of X-ray sources. So we use a machine learning pipeline, which was talked about in detail by Hui Yang on August 19 to classify X-ray sources. In summary, it uses multi-wavelength data from Chandra, Gaia, 2 mass and Wise, and it uses a random forest classification algorithm. 31 features, including Chandra fluxes, variability features, photometry colors, and it samples uncertainties. Our training data says about 3,000 sources over 9 classes. So one feature that we did not use in the past was distances. It's an important parameter in classification, and it's used to determine source luminosities, but it's difficult to incorporate into training data sets because it's not available for many sources, and parallax-derived distances often have large uncertainties. So recently, Gaia EDR3 distances were calculated by Baylor Jones and their group. It includes 2 sets of distance measurements, RGO, which depends only on parallax and source direction in the skies, and RPGO, which also depends on Gaia Gmag and BP minus RP color. The priors that calculate these distances assume only single stellar sources, so these distances aren't reliable for binaries, AGNs, and other exotic sources. These distances are available for about 2/3 of sources in our training data set, and confident distances are available for only about 1/3 of sources. So if we include these distances into our machine learning pipeline, we see that the pipeline treats the distance by itself as this 3rd most important feature. If we also add the associated luminosities in infrared, optical, and X-ray, we see that these distance-dependent features are about as important as some of the other magnitudes that we use. When we run the pipeline on our training data set, we get these confusion matrices. We see the predicted classes on the bottom here, and we see the true classes of the sources on the side. And when we run the pipeline with no distance information and with distance information with luminosity, we see if we blink back and forth here, we see that for some classes, there is indeed an increase in accuracy for our training data set, including CVs, high mass stars, HMXBs, and low mass stars. In particular, low mass stars increased by 4% with only 1% on uncertainty.
2 minutes.
So we found that adding either set of distances provide a slight increase in accuracy, and adding luminosities on top of that further increase the accuracy a bit more. We also found that Gaia EDR3 parallaxes perform similarly to distances. Then we evaluated the pipeline on field data. So this is NGC 3532. It's an open cluster 500 parsecs away, and it's about 300 million years old. So when we evaluated the pipeline on this cluster, we get the number of confidence sources per class for each of the distance metrics that we used. So we see for most of the classes here, there's not that many sources confidently classified, and there's not that much of a change between the different distance metrics and no distance. Most significant change were for low mass stars. We see that using any distance metric increases the number of confidently classified low mass stars by over 10% compared to not using distance at all. So in summary, about a third of the X-ray sources in this field were classified confidently. And also we found that adding distance information increases the classification probability slightly as well. And in conclusion, we found that adding distances as features do improve accuracy and performance of our machine learning pipeline. And in the future, we will continue to explore more reliable distances to add into our pipeline, as well as other features like Gaia proper motions and galactic coordinates. Thank you, and I'll take any questions.
Thank you, Steve. I'm sorry, Stephen. I think we have time for one question that I'll ask you, and other people, you can put your questions in the Slack if you have a question for Stephen. So you do have a lot of binaries in your sample, and so you're using. You mentioned that the distances were from the Baylor-Jones distances were not reliable for those.
Right.
How are you dealing with that?
So the Baylor-Jones distances came with like upper and lower confident bounds. So we did a cut on those. We did a cut on only confident distances, basically. There might be. Sorry.
I was going to say, if you've looked to see if there's anything that sticks out in the RUI, the renormalized weight error, or the excess astrometric noise in your samples.
I think those questions might be better referred for Wei Yang.
Great.
Who did most of the work on the pipeline itself.
Yeah. Thank you. Thank you for your talk. And our next speaker, if you can begin sharing your slides. Our next speaker is Lucia Härer, and is joining us from Dr. Karl-Remeis Observatory, University of Erlangen-Nürnberg, and is going to talk to us about stellar wind variability in Cyg X-1 from high resolution excess variance spectroscopy with Chandra.
Yeah, thanks for the introduction. Yeah, I'm very glad for the opportunity to present my work here. I'm Lucia Härer, as already introduced, from the Dr. Karl-Remeis Observatory in Bamberg. And part of this project I also did as a NISA trainee. And yeah, I will talk about high resolution excess variance spectroscopy of the stellar wind in Cygnus X-1. Stellar winds of massive stars are very strong. And the winds are also highly structured. And this structure leads to an overestimation of the mass loss of these winds by a factor of 2 to 10, which is quite large, and also introduces quite large uncertainties on stellar evolution models, and in general impacts various things because of the importance of massive stars and their feedback in general. Stellar winds of massive stars can be probed in high-mass X-ray binaries. And what is done there is we can use the X-ray emission from the compact object as a backlight to study the absorption in the wind. And the structure in particular can be studied from the variability of the column density. And I want to highlight one result here from Ilek Elmela, Victoria Greenberg et al., with whom I've also worked on this project. Namely, they devised a model and showed that statistical properties of the variability can be used to infer masses and sizes of clumps that the stellar wind consists of, as shown over here, the model. The source I've been looking at is Cygnus X-1, that's a high-mass X-ray binary. It has a quite low orbital separation, and as you can see in this artist's impression, this introduces a focused stream of material via which the black hole accretes in addition to the wind accretion. The inclination is just below 30 degrees, so the source is not obscured, and we have this line of sight. Cygnus X-1 has high absorption variability, especially in its low hard state. This is believed to be introduced by the structure of the stellar wind. Variability can be studied with a number of techniques, but what we applied is fractional excess variance. And this is the variance of a light curve above the statistical Poisson noise normalized by the mean number of counts. And so as a result, this quantity is indicative of the true physical variability in the source. And we can also calculate this now as a function of energy or wavelength and construct an excess variance spectrum. I've used this technique previously in a project with Michael Parker to study AGN ultrafast outflows, which were also mentioned in the first talk today. These outflows are usually detected via highly blue-shifted absorption lines in the count spectrum, as you can see, for example, over here. And but these lines also show an increased variability, which introduces spikes in the variance spectrum. And that can be used to detect these ultrafast outflows, investigate their structure, and also do modeling, as I did in this previous project. So there in this project, I worked with CCD data, but of course, it's interesting to go to higher spectral resolutions. And to do this with excess variance, we need an object with a high signal, and this is why we chose Cygnus X-1 kind of to try out what we can do with this method at higher spectral resolutions. And yeah, as we looked at Cygnus X-1, we looked at two observations, one at superior conjunction and one at inferior conjunction. And the light curves from these observations are a bit different. Namely, at superior conjunctions, we see these dips, and each dip is believed to be associated with the passage of one clump in the stellar wind across the line of sight. And these are predominantly at superior conjunction, and the inferior conjunction light curve is more constant. These observations have previously been analyzed in a paper series by Hanke et al., Miskobikova et al., and Hirsch et al. And this is great because we can then compare it to their results, which I will also now do later in the talk. And yeah, I think I didn't mention this so far. So these observations were taken with Chandra. It turns out that working with gratings data to do excess variance spectroscopy introduces several systematics that have to be taken care of. I want to focus on a particular example here, namely the variance that is introduced by CCD gaps. What you can see here is an image, basically is data in detector coordinates. So these here, the panels you can see here are the individual CCDs of the ACIS detector. And between these CCDs, there are gaps. And there are also, as you can see here in the zoom in, there are also smaller dead pixel columns. And because the instrument dithers, the intensity of the measured X-rays around these gaps strongly varies. And this then introduces huge spikes in the excess variance. And we filtered these out, all the affected regions. Basically, all the red regions here are affected by this gap variability. And as you can see down here, this worked quite well, and excluding this huge spike from the CCD gap and also the smaller spikes. As a consequence, the sensitivity is reduced in specific regions by quite a large factor because we basically have to cut out this region for a specific gratings arm. Okay, with the systematics taken care of, we can now talk about the results. And this is what you can see over here. So in blue is shown the superior conjunction observation, and in red, the inferior conjunction observation. And already at first glance, you can notice a huge qualitative difference. Namely, the inferior conjunction continuum is consistent with 0, while the superior conjunction continuum increases approximately linearly. And also in the superior conjunction continuum, there are features. And especially you might notice this feature here just below 7 keV, angstrom, sorry. And this region actually corresponds to the silicon line region, which was used by Hirsch et al. To study the ionization of the material in the wind, depending on the depth of the dip in the light curve that I showed you before. And from this study, they devised that for the spectrum, this corresponds to the deepest dipping stages, the ionization is lower than in the non-dip spectrum, which means that the clumps have an ionization structure. Going back to the results, we can now look at this superior conjunction observation in more detail. And this now shows the results relative to the continuum with the lines from the Hirsch et al. Study highlighted in orange, and also from the lines from the other papers of the series highlighted in black and gray here. And you can see that this spike here splits up into several smaller spikes, which correspond to the positions of the known lines. And we see a similar correspondence also in other regions. For example, there's some correspondence for neon in general, but it's not as significant. The biggest significance is definitely in the silicon line region. Let's look at it. Let's look at this region in a bit more detail still. Here plotted below is the count spectrum for comparison, and there you can see that the spike and line positions really match well, and that also their strength matches to the strength of the spikes. We obtained a similar result for the sulfur line region, although this is less significant due to the gap filtering, which I described before, which by chance affected this region. From this, we conclude that the spikes are probably caused by some variability that is intrinsic to the lines. From the clear correspondence that we see. So from these results, I want to now raise two questions that I will then discuss in the following. Namely, first of all, can absorption in the clumpy wind explain the variability we observe? And then can this be used to actually characterize the structure of the clumpy wind? Because as I motivated before, understanding the structure is important to understand to update mass loss estimates. And we did this by a modeling approach, and this was based on the clumpy wind model that I talked about in the beginning by Emissivity et al. Here the clumps are, the wind is assumed to consist of spherical clumps that move outwards and accelerate and also grow. And from this model, we obtain NH light curves. And these light curves we can then feed in a model which creates absorbed model spectra. And from this, we can then calculate the excess variance spectrum. Here you can see a side-by-side comparison of the model and the data. The model is on the left side. And as you can see here, the strong line of sight effect is well reproduced by the model. Or at least it is so for a high beta, which means that the wind is gradually accelerating. Also, this continuum here falls off a bit faster than in the data, but there's still a large line of sight effect, and the predicted variability also really well matches the measured variability. There are also spikes present in the model, and also weak spikes at inferior conjunction, but there are several effects that can suppress the variability in the data that are not accounted for in the model. For example, that we see p Cygni profiles at inferior conjunction, and also that we had to rebin the data to gain enough signal to do the analysis. In this model, the mechanism by which the increased line variability is produced is that the line strength is anti-correlated with the continuum. And basically, this means that if there's more material between the X-ray source and the observer, then the continuum will decrease, but the line strength will increase. And as a result, the variability in the line in total will increase, and this is what gives you these spikes. And in general, we conclude that there's a good qualitative agreement between the model and the data, and that variability from a clumpy wind can plausibly explain the variability we observe in Cygnus X-1. One factor that I haven't much talked about so far is ionization. For our model, we fixed ionization at a certain value, but in reality, the ionization structure is really complex. This is what this figure shows up here. Here you can see the population of different iron species. And shown down here is here's the ionization parameter. This can be translated in a distance from the X-ray source. And then with knowledge of the location of the observer from Miskovikova et al., we can conclude that we expect the ionization to vary over this whole range. And in addition to that, I mentioned earlier that we know that the clumps have a layered ionization structure. And so we know ionization will definitely vary in the absorber. And from the study of ultra-fast outflows, we also know that ionization is very likely to introduce additional variability and also introduce increased line variability. But to take the effect into account in the complex case for Cygnus X-1, radiative transfer modeling would be required, which we might do as a next step. The second question I raised was about whether we can infer wind structure from the excess variance. And here is a plot that shows that our model results strongly depend on this ratio here of the clump mass and its radius. This is no new result. This comes out of the clumpy wind model that we use as a basis for our model. But still, it is quite nice to see that we have a strong dependence here, and it also means that future versions of the model might be able to fit this parameter. But still, this only gives a ratio of the clump mass and radius. If we want to disentangle these two parameters, we need an additional tool, namely timescale measurements. And we have also done this in the data of Cygnus X-1. And with the excess variance, the timescale can be investigated by changing the binning of the light curve, because the binning basically determines the upper frequency bound of frequencies that contribute to the excess variance. So if we increase the binning time step, the excess variance falls off. And this is expected because higher frequencies are excluded as we go to higher binning time steps.
2 minutes.
And yeah, thanks. And we also compared the region where we don't see lines to the silicon line region. And interestingly, the trend here is a bit flatter. So it might point to an effect where the variability is introduced by larger clumps, or larger clumps contribute more to the variability, I should say. And this might be because because in larger clumps, the line strength can vary over a wider range. So this brings me to my summary. Massive stars have strong clumpy winds, and this clumpiness hampers the accuracy of mass loss estimates. Excess variance spectroscopy at high resolution, as we demonstrated with Chandra gratings data, can study the variability in individual spectral lines. In the result for the silicon region I showed up here. There are several systematic effects that can be taken care of. The largest one comes from the CCD gaps. In general, we see in Cygnus X-1 a strong line of sight dependence and enhanced line variability, which is well reproduced by the model. And in the end, I talked a little bit about an outlook. I want to stress the third point here, namely that with microcalorimetry missions, such as CRISM and Athena, the sensitivity will very greatly increase, and we will have a comparable or better resolution. And this means that high resolution excess variance spectroscopy will be available for a far greater number of sources, also including AGN. Okay, with this, I'm at the end of my talk. 2 more remarks. If you're interested, the clumpy wind model is available on request. And also we are preparing a paper which is going to be submitted very soon. Yeah, I'm happy to take questions.
Thank you, Lucia, for that great talk. If you have any questions, please put them into the Slack or the Q&A here. I'm going to ask you a question about the definition of the excess variance. Whenever I may have missed it, but when you're dividing by the mean counts, is it the mean count? It's the mean counts in the bin that you're studying, right?
Yeah.
Or is it?
Right.
Okay, good. That's all I wanted to verify, actually, because I was trying to get it straight in my mind. The other question I had is about when you start talking about the time temporal part. Did you look at the gaps, the features that were created by the gaps, and see if they verify with what you'd expect from the dither pattern and timescale?
No, we didn't really check for the time dependence of those features. But you can see this gray region here in the plot. This is where we would expect some features if they were present from the dithering. So this is basically the time range for the dithering.
Okay, cool. Any other questions? No more questions.
Yeah, I'm also in Slack if something else comes up.
Yeah. Great work. It's very interesting to see, and it really, I think, powerful use of the gratings. I love seeing detector coordinates images. We seldom see them, but I really enjoy it because it really reminds me that the spacecraft is actually moving the whole time.
Yeah.
Okay. Thank you again for the excellent talk. If you have any questions, please put them in the Slack where you can find Lucia. Our next speaker, if you can begin, make sure we can share your slides. Our next speaker is Xixi from Imperial College London, and is going to talk to us about the effect of systematic uncertainties on density and temperature estimates in the Coronae of Capella.
Hi everyone, can you hear me well?
Yes.
Okay, So I'm going to talk about my work relating to the effect of systematic uncertainties on density and temperature estimates in the stellar spectral analyses. Specifically, we focus on the Capella study. Actually, before this work, this is the second part of our work. For the first part, we are trying to incorporate atomic data uncertainties into the solar spectral analysis via a case study on iron 13. This is a roadmap. The roadmap. So in the first part, it's about the solar spectral analysis study on iron 13, where the atomic data is temperature insensitive. So we focus on the estimation of plasma density. And then now we come to the second part. So we work on the stellar spectral analysis on Capella, where we incorporate the uncertainty of atomic data into the iron 17 spectral analysis, where the atomic data is, in this case, is density insensitive, but instead we're focusing on the estimate of plasma temperature. With this analysis, we will work on another analysis on oxygen 7, where the different part is the atomic data for oxygen 7 that is both density and temperature sensitive. So we will incorporate the previous information about temperature from iron 17, incorporate it into our analysis on oxygen 7. Yeah, so this is pretty much about the work in this talk. And because the complexity of the structure of stellar corona, we want to measure the physical quantities of stellar atmosphere like density, temperature. In the meanwhile, we observe the photon counts. However, those information about physical properties of the astrophysical objects cannot be measured directly, but we need to it need to be inferred by interpreting the spectroscopic observations in the context of atomic physics calculation. So a critical component of this analysis is understanding how uncertainties in the underlying atomic physics propagates to the uncertainties in the inferred plasma parameters. From an astrophysical point of view, even though it is well known that the atomic uncertainty do exist, and it is recognized that these atomic uncertainties can cause large systematical errors in the inferred model parameter, those uncertainties are often taken on face, with only nominal estimates are used in the data analysis. So the most commonly used method, we call it standard method, is we treat those uncertainties as fixed and known. So we know, for example, a method is chi-square minimization. So after using it, we are able to obtain the best fit values of those plasma parameters. However, such standard method would introduce bias in the estimation of model parameters and result in underestimation of the variance of these plasma parameter estimation, and may in the end lead to erroneous interpretation of the data. So before we move on to the statistical methodology, I'd like to talk a little bit more about the atomic uncertainty, which is the emissivity. It is how much energy is radiated from a unit volume of plasma at given level of at given density and temperature, and it is calculated from a model accounting for uncertainty in atomic data for specific ion like iron 17 and oxygen 7 in this study. We can denote the collection of emissivity realizations as capital M, and we always put M equal to 1. Lowercase m represent each of the emissivity curves, and we always put lowercase m equal to 1. That's the default emissivity curves. We also use the Gaussian approximation via PCA principal component analysis to efficiently represent the high-dimensional complex distribution of the emissivity uncertainty. Okay, now we come to a statistical perspective. From a statistical perspective, we aim to propose a multi-stage analysis to incorporate those atomic data uncertainty in emissivity and to estimate, in the end, to estimate the plasma density and temperature. We start from a simple case, which is a two-stage analysis. In the first stage, the atomic data epsilon is estimated from the information in the analysis of the first data set. We use X, denoted in X here. But this data set X may be unavailable to the following in the following stage. So in the following stage, we call it primary stage. We estimate the plasma parameters and also the emissivities given the new data set, which is typically the observed photon counts, for example. And then we are able to design, we aim to design this robust principal method, and in the end to estimate the plasma parameter via the observed photon count, the analysis on observed photon counts. And in the meanwhile, it still depends on emissivity of atomic data that can be first initially estimated in the preliminary stage. And then we are able to account for the emissivity uncertainty and when we try to estimate the stellar parameters. And so in summary, the general idea of this multi-stage analysis is the output from the preliminary analysis is required for the primary analysis. We have incorporate three different statistical methodologies. The first one is the most commonly used one, the standard methodology, where we assume the epsilon, which is the emissivity, to be the best fit estimate from the preliminary analysis. In this case, we didn't account for any uncertainty in the atomic data. So to eliminate these disadvantages, we want to fit the spectral parameters given the observed photon counts, while in the meanwhile still account for atomic uncertainties. In this case, we adopt a Bayesian framework in our statistical analysis, and these two Bayesian methodology has been mentioned by my supervisor's talk, David, in the earlier section today. So for the first method, it is the pragmatic Bayesian method. Basically, we don't want the emissivities, we don't want the observed photon counts to provide any information to the choice of emissivities. This is an assumption for pragmatic Bayesian method. And then for the fully Bayesian method, instead of using this assumption, we eliminate it. And so we would like the observed photon counts to provide information on the choice of emissivities. So this is the major difference about the two methods, two Bayesian methods. Next, here is a summary of the data parameter and emissivities used in this work. We have two data sets basically in two different stages. The first stage, we have the iron 17 photon counts. Specifically in this iron 17 spectral analysis, density is insensitive. It is insensitive to density, so we have temperature parameter considered only. And in the oxygen analysis, we have the oxygen 7 photon counts, and in the meanwhile, the spectral model is sensitive to both density and temperature. For simplicity, we summarize the parameters into three sets. So theta iron, that represents the parameter only exists in ion 17 model, and theta oxygen that represents the parameter that only exists in oxygen model. And then theta oxygen and ion that represents a common parameter that exists in both ion 17 and oxygen 7 model. And then we have a collection of emissivity realizations. Each realization is denoted by epsilon. Specifically in our work, we are approximating the corona with a single density and single temperature plasma. But in reality, there will be an array of plasma volumes of different density and different temperatures involved. So to start with, we start from a simple two-stage analysis on ion 17, and we focus our attention on the primary stage, where we use the two Bayesian methods to incorporate the information in data to narrow the uncertainty in the atomic physics, and then in the end to narrow the uncertainty in the plasma parameters. For the pragmatic Bayesian method, we assume that we do not take account any information in the data for the choice of emissivities, as highlighted in blue here, and then the joint posterior distribution for emissivity and the plasma parameter under the pragmatic Bayesian model is in equation 4. And then in contrast to the pragmatic Bayesian model, the fully Bayesian method incorporates the perceptual information in the observed photon counts to learn about the emissivity. So the fully Bayesian joint posterior distribution can be expressed in equation 5. Specifically, we expect that the variance of emissivity given the observed photon counts is smaller than the variance of emissivity itself. So reducing the variance in atomic data will in the end result in the reduction in the uncertainty of fitted stellar parameters. With the pragmatic and fully Bayesian setup already, we do the analysis on the ion 17 observed photon counts. Here in this figure, we are comparing the posterior samples from pragmatic Bayesian model in green lines and compare that with the posterior samples under the fully Bayesian models in the amber curve. Each panel is for a specific parameter, like alpha 1 represents the electron temperature, log alpha 0 is the normalization parameter, and we have incorporated 7 principal components to summarize the ion 17 emissivities. So we noticed that incorporating the uncertainty of emissivity under the pragmatic Bayesian model will introduce large error bars compared to the case where we don't consider the uncertainty of emissivities. Well, on the other hand, the fully Bayesian model is shrinking the error bars compared to the pragmatic Bayesian model. And also for the posterior samples like density, like temperature in this case, and normalization parameter, we can see there are gaps between the pragmatic Bayesian results and the fully Bayesian results, and also the error bars got shrinked under the fully Bayesian model. So this indicates that this is sensitive to this parameter estimation is sensitive to the choice of emissivities, and the data, the observed photon counts, is more informative about the emissivities than our prior knowledge about it. So next, using the parameter estimation under the fully Bayesian model, we are able to calculate the best fit emissivities. In this figure, we can see we are showing the emissivities. We have 1,000 emissivity realizations for the all 13 iron 17 wavelengths. They are in gray. They are the gray curves, and we also plot the default emissivities for each of the lines in green curve, and also we have the best fit emissivities in red curve, which is calculated from the best fit plasma parameters under the fully.
2 minutes.
Okay, under the fully Bayesian model. So the next one, we are also calculate using the fully Bayesian results. We are able to calculate the spectrum. So the middle panel is like a zoom-in version for each of the lines of interest. We can see using the best fit parameters, we are able to we are able to get a best fit good fit to the spectrum. And then we are able to summarize the posterior samples of the temperature and density, temperature and normalization parameter. We use two approximation distributions: Gaussian in the amber contour, and the multivariate T distribution approximation, which is in green. And we can see the solid curve is for the 68% mass of the total distribution, and then the dash contours are for the 95%. We can see the T distribution approximation has a relatively heavier tails, which is conservative as expected. So we are going to use it as the prior distribution for the next one, oxygen distribution. In the oxygen distribution, it's a little bit more complicated. It has 3 stages. Besides the atomic data, preliminary stage on atomic data, we also use the analysis on iron 17 to use the posterior distribution from iron 17 spectral analysis, use it as the prior for oxygen analysis. Similarly, we also consider the pragmatic and fully Bayesian model on the emissivities in the primary stage. Similarly, we do the fully Bayesian model, and we compare the fully Bayesian results and the pragmatic Bayesian results. And under the fully Bayesian model, the error bars shrink a little bit compared to the pragmatic Bayesian model. And then using the fully Bayesian results, we are able to calculate the best fit emissivities. It is the red curve again. But in this case, because the oxygen 7 emissivities is both density and temperature dependent. So in this, along the axis, the temperature is increasing, and then within each panel, the density is increasing for this plot. So in the end, we are also able to use the best fit parameters to calculate the spectrum. We can see, again, we get a perfect fit for the spectrum. In this figure, we are actually comparing the expected counts using the parameter posterior samples under the fully Bayesian model, and then compare that with the observed photon counts, which is the blue histograms behind. We can see we get a perfect fit. So in summary, we are able to embed the Bayesian frameworks into this multi-stage analysis to incorporate the atomic data uncertainty into the stellar spectral analysis. And then the fully Bayesian method is able to shrink the error bars relative to the pragmatic Bayesian methods, and also shift the best fit estimate because it selects a subset of atomic uncertainties that is more consistent with the observed photon counts. Okay, so this is pretty much about my talk, and now I'm okay to take any questions.
Thank you, Xixi. Do we have any questions for our speaker? I think we maybe have one coming right now. I wanted to remark about this problem about the iron emission. I study planetary nebulae, and they're iron deficient X-ray plasmas. And iron is actually gets in the way a lot of times when I'm studying them. Doesn't allow me to fit get a reasonable fit unless I turn the iron abundance way down. Would a source like that be interesting for tackling the oxygen emissivities?
Sorry, could you please repeat your questions?
If you had a plasma that was iron deficient, would it be interesting for trying to constrain the emissivities in oxygen without the iron priors?
I think in this case, because I hope I understand your question. So because in this case, the initial study on the pragmatic Bayesian method, it is actually it's assuming that we don't have any prior knowledge about the emissivities, so the observed photon counts would not provide any information on those data. So this is about the pragmatic Bayesian method. But for the fully Bayesian method, we do let the data to provide information on our choice of emissivities. And then according to the results in this plot, we can see we do have smaller error bars for under the fully Bayesian model compared to the pragmatic Bayesian model. And then that indicates that the data does provide information to let us to choose a small subset of emissivities, and those emissivities would contribute more to the estimation of parameter. And then, so in summary, we say the observed, some of this subset of emissivities is more plausible given the observed photon counts. Is this answer your question?
Maybe, yeah, maybe. I have to think about it. We have a question from Douglas Busson, who says, if the full rather than pragmatic Bayes gives a much better constraint, does this really mean that you improve the atomic estimates, or actually that the rest of the model is too restrictive? And they add a note that they suspect this may be a matter of background knowledge / judgment, maybe for their question.
So under the fully Bayesian model, we are able to select a subset of emissivities, which is supported by the observed photon counts, either in oxygen 7 or iron 17 ions. So that means we can provide more accurate estimate on the plasma parameters. Then we don't let the observed photon counts to provide information.
Great. Okay, there's no more questions. I think that's all the time we have for questions for your talk as well. If you have any more questions, put them in the Slack. And thank you again for your talk, Xixi.
Thank you.
Our next and last final session talk is more of a closing remarks kind of talk, not necessarily a summary, but a discussion. And I'd like to invite everyone to remember our chair of the Science Organizing Committee, Moritz, we're gonna talk a little bit about the workshop, and then we're gonna have a special SOC member guest, Rafael Martinez Galarza, who you probably have all seen asking all the questions. Give a little bit of a summary, not summary, but a little talk about some of the big topics that came up and their potential for discovery. I'd like to start by actually thanking Moritz for the idea for this whole workshop. Many of you may not know this, but I fielded requests from the CXC community for ideas on workshops, and this is the one that rose to the top right away. That was provided by Moritz to talk about this, all of these efforts that the community have been making to develop these outstanding techniques that really help us maximize the scientific potential of the data. Moritz, do you have anything you want to add to that?
I want to yeah, I want to take first the opportunity to thank Rudy to organize it all, because he's done most of it. But I thought this conference, this conference worked out really well, like very, very close to what I had in mind when I suggested it initially. And one thing that Chandra conferences usually do is they try to find something that's common to all areas of X-ray astrophysics. And that's really hard. Like, I've been in a meeting about jets on different scales or something, where you talk about jets from brown dwarfs, jets from AGN, and that's all jets, and there's some similarities, but it actually turns out they're very different in many respects. And so this time, I think what's good about this is that it's like machine learning, and then these types of statistical analysis are pretty new. Like, I know that many of you have been working on them for several years, but it's not something that was around in this thing when Chandra launched, right? Even if a couple of you have worked on it for a long time, for most of us, it's a rapidly developing field. And many of these techniques are actually applicable to a wide range of astrophysics. But we didn't want a methods conference. We didn't want a conference about statistics. We want a conference about astrophysics. And I think like all the talks, or essentially almost all talks, have done a very good job of like showing a method and how it's used for astrophysics, but describing the method well enough that I could go, oh, how can I do that for stars? Is that useful for me? And still like getting astrophysical results in some way. And so that was my hope when I suggested it. And I think that Chandra Director's office has wisely chosen to pick this topic. And I hope that all of you who've listened to talks that ran, let's say, about planetary nebula or AGN or whatever the topics you work on, have still learned something from the other methods to take off. And I think it worked out really well. I want to thank the speakers. I want to thank the SOC for selecting, right, and the speakers for giving awesome talks who really brought this vision to life. I think that's been very valuable.
Yeah, I want to echo that comment about thinking about what you can do with it, that the talks were presented on that level. A couple of times I got in trouble by thinking too much about what I want to do with what they were talking about, and then trying to catch back up with the talk. Great.
Unfortunately, it's recorded, so we can always go back and look at it a second time.
It's recorded.
I'll certainly go back and look on more of the things that we have on the YouTube that I either missed or didn't fully catch while they were ongoing.
And that's a good point to raise. All of the talks are recorded. We will be updating the website to have little YouTube links next to all of the sessions, so you can go straight to that session if you're interested in listening to a particular session again. So I think maybe we'll introduce Raphael, let Raphael speak for a bit now, in 5 or 7 minutes, and then we're going to wrap up once again by putting up a slide of all the SOC and thanking them again, and the subcommittees as well. So go ahead, Raphael.
Sorry, I always have trouble unmuting myself here. Can you hear me?
Yes, I can.
All right. So I don't want to take too much of your time. I know everyone's eager to go to either lunch or dinner or breakfast, depending on when you are. I just wanted to keep you for 5 more minutes to share a few thoughts about what I've seen and what I've learned in this conference in a very general context. And by the way, for those of you who go on Twitter, you can find some of the tweets that I made during the conference in that hashtag that you see there in the screen, in case someone sees this. I still have to update the lay ones. So basically, one first thing I want to say is I think Moritz put it in a good way. These methods aren't new; they are new to us. Before I came to this conference, I was under the impression that the X-ray community was a little bit behind in the usage of these methods of statistical analysis, machine learning, Bayesian statistics, etc., etc. I leave with a very different impression. I think we've really caught up with all these methods and we're doing very, very well. And all I want to do here is go over a couple of very, very general ideas and methods that were discussed here and see what that means in terms of what we can do and what we cannot do in the future. So one thing is machine learning. Of course, we've learned this. It spells magic for some. It spells some reactions to others. But I think the fact that we've heard so many talks during this conference about machine learning, it's saying something. And I think the reason for that is basically that, or at least one of the main reasons, is that the volume of our data is increasing. We have new missions, we have existing missions that take more and more data, and we also have catalogs. And catalogs like the Chandra source catalog, like the XMM catalog, like the Cyg catalog, and the upcoming eROSITA catalog provide us with a new plethora of data that we can explore. And we heard in this conference talks of machine learning used, for example, for classification of X-ray sources. We also heard talks about rejecting background photons using machine learning. We heard talks about encoding cosmological models with machine learning, separating components in X-ray spectral images using machine learning, identifying multiple wavelength counterparts of machine learning, etc., etc. So that is something that is very, very telling about the power of this. And however, I think one big message that we should all take from this is use machine learning with cautions, under the supervision of an adult, and do not overinterpret it. I mean, it can be extremely useful if you have a large amount of data. We tend to think that as X-ray astronomers that we don't have a lot of data because we detect individual photons, but we are starting to learn how to do, for example, the analysis of individual photon arrivals using machine learning, and that's extremely interesting, such as in the case of separating sources in an X-ray image. So keep all this in mind. Be careful with the way you use it. Be careful of your training sets. Make sure that when you use supervised learning, those training sets are representative, and don't overinterpret this. But this list of things give you an idea of the extreme potential that we have in machine learning. We also heard a lot about Bayesian analysis, and this was brought up in several contexts early on in the conference, in the context of spectral analysis for fitting spectra, X-ray spectra in the low count regime. And this, I think, it's extremely useful, in particular from the point of view of model comparison. As X-ray astronomers, we do a lot of X-ray spectral fitting analysis using, for example, XSpec or Sherpa, but very rarely we stop to think about things like uncertainties and how well constrained our parameters are in that regime. I think the fact that we had very healthy and useful discussions about how to compare models and how to select a model over other, if you can actually do that using all the evidence you have in your data and any previous knowledge that you have, it's a very extremely useful message from this conference that you should all keep in mind. Fit your spectra, but try to keep in mind the uncertainties and how much information you actually have from your data by using these methods of uncertainty estimation. We also heard interesting, and I was mentioning this earlier, about disentangling confused sources using spectral and timing information using Bayesian techniques, and that goes towards the thing that I said before. We can now take information from single photons arrivals and do Bayesian analysis on those and use that to make what was previously considered impossible, like such as separating sources in an X-ray image that are very confused. That's extremely important, and we should all keep an eye on those developments. But one thing, yes, one thing that I think we should have in mind is where all these priors come from, the priors that we use to inform our models. In a lot of cases, those priors come from looking at other wavelengths. And I think this conference should also be an opportunity for you to think in a multi-wavelength way. The information that you don't have from the X-rays, many times you have from the optical or infrared data. And it's important for us to use these techniques that unify us as X-rays astronomers to also reach out to communities outside of X-ray world and try to get additional information from there. And finally, the last thing I want to say is about catalogs, variability, and future discovery. I think the fact that we now have very, very rich catalogs of X-ray sources, as I mentioned before, is opening the possibility for a lot of research in terms of X-ray time domain. Last year's conference was actually about time domain. I think we should all realize that this is the case. We heard excellent talks during this conference about studying variability, both in short time scales in the duration of a single observation, and also in longer time scales by comparing observation to observation. And I encourage you all to use all the many serendipitous detections that we've done in these wonderful catalogs to do astronomical discovery. Flares, lensing events, etc., etc. They're all hidden in these catalogs, and we now have the tools to do that. We actually heard about all those tools as well, how to estimate variability in the Poisson regime. How do you say if something's variable or not when you only have a few photons that are arriving in your detector? Those are all ideas that came from this workshop, and I encourage you all to review them. And of course, because we have all those serendipitous sources, we also need to think in terms of anomaly detection for discovery. I think it's important for us to realize that there are existing methods that allow us to find those objects that are unlike any others in these wonderful catalogs. And I encourage you all to investigate about those and to look forward for future discoveries. So those were my general ideas. I didn't want to take too much time. I only want to say thank you, Rudy and Moritz, for this organization, for this wonderful conference. And I hope that in the future, we will keep going the collaborations on these different techniques for the discovery in the X-ray world. Thanks.
Thank you, Rafael. That was excellent. What I'm showing you here is the SOC, because I want to thank them again profusely for all of their help in setting up and organizing everything. It was difficult to select the SOC because every one of these people could have been up here giving you an excellent talk, and they had to make a sacrifice about whether they could be given a talk or whether they would help us organize and facilitate this conference. So I really want to thank them very much again for stepping up to serve on the SOC. I also want to thank our special sessions subcommittee, which brought you those 2 coffees. I hope you enjoyed them. And if you like that kind of stuff, I will be sending around a survey about next week after our tutorials, asking you for your feedback on how various aspects of the workshop. So please keep an eye out for that and submit that survey. And the last thing I want to point out to you is remind you once again that the self-organized tutorials are happening next week, Monday, Tuesday, Wednesday, in the morning here on the East Coast, 9 a.m. to 11 a.m. with a 15-minute break in between. If you want more information on that, look in your email for the form to express your interest in attending those. Moritz, do you have anything you want to add?
Well, thanks to the people who listened, because the conference is only so good if it actually is attended by someone, right? And I think we had a lot of thoughtful questions. The Slack stays open, right? So you can continue to connect to the speakers there. We're not going to delete it like in the foreseeable future. You can continue to connect with the speakers and or with each other and see what it's good for. And also with Rudy and me, if you have beyond the survey some more feedback, because Chandra organizes conferences annually. This is only the second one that's been taken place online. So that's like any comment on how that worked, or like small things, slides too big, Rudy speaking too loud, I don't know, something like that is going to be very helpful because Chandra will, of course, the Chandra X-ray Center will have to decide how to do that in the future. And so while it's still fresh in your mind, please write something down.
Yep. A lot of the changes in this session, in this virtual workshop, came from the first one, the form that we had in the first one. So I'm especially excited to hear if my voice is too loud.
No, it's not.
First.
It's not, but.
Okay. And I also want to thank finally Tara Gokas, who had to leave just now, and Evan Tingle, who are the CDO techs who have been helping me with the slide, sharing the slides and the Zoom sessions and everything for the whole week. Without them, I couldn't do it, or I'd be too distracted to stay focused. And thanks again, Moritz. This has been excellent working with you. Thanks, everybody else. Hope to see you next week at the tutorials. Bye.
Thank you. Bye.